So let's talk about integration. So what is integration? Well, most people will tell you it's the opposite of differentiation. And some notation first. So this is how you write the integral. It's like an S, it's like a curly long S, and then you have the function in here, whatever that is. And then you have the dx again. So that means with respect to x. And then you get a value over here. And depending on the function, you get different values on the right hand side right here. So this is just right hand side. So, what is integration useful for? So remember, if you have a curve, once again, with lines everything is easy, but when it comes to curves, we need some more tools. So let's say we had a curve that looked like that, right? Something like that. Now we know how to find the gradient at any point. We can draw a tangent. We can find the gradient at any point we want. But let's forget about the gradient. Let's say we wanted to find, for some reason, the area underneath the curve. So let's say we wanted to find the area between this and this point. So let's say that point is A and that point is B. Let's say we wanted to find the area of this region right here inside. How would we do that? Well, one thing that we can do is let's say we can make like rectangles, right? Let's say we had a rectangle that looked like that, and then another rectangle that looked like that, and then another one that looks something like this. And then you can like approximate with rectangles. You can make them as short as you want, as long as you want. Let's say those were our rectangles, right? That would get us pretty close to the area. Like, we would almost get the exact area, but of course it won't be precise because, rectangles are basically straight lines and we have a curve. So it's impossible to just get it by only doing rectangles. But what if we kept on making like the width extremely small? So like it was very, very small, and then we drew the line again. And then again, very, very small, and then do another rectangle. So now you can see we would have many rectangles, and they would give us a better approximation of the area underneath this curve right here between the region between A and B. And there's like a formal way to get the proof and everything, but I'll just tell you. So let's say this curve was y is equal to x squared plus 2x, right? The way you would get the area underneath the curve is you would integrate, so that's the integral sign, and then you have the function right here. So you have the curve x squared plus 2x, and then you have dx, of course, right? So this is one thing and dx is the other thing. This just means with respect to x. This comes in very useful later on. And you want to do it between a and b. So b is your upper bound and a is your lower bound. So what this is telling you is that when you actually calculate this, you'll get the area of the curve between a and b, and the curve is x squared plus 2x, and this will be the exact area. And the way you do it is, so you have to find a function that when you differentiate gives you y. So now you have y, right? If you differentiated this, you would get 2x plus 2. But now I want something else that when I differentiate that, I get x squared plus 2x. So it's like y is the derivative already. So we need to find the integral of y. Well, how do you do that? For the derivative, from the power rule, remember, we bring the power down, multiply by the thing, and then reduce the power by 1, right? Well, for the integral, we go in reverse. So now we have the power 2 right here. So we bring the power up by 1, 3, and then we divide by the power, which is 3. And we can do it for 2x. So that's 2x to the power 1. So now what we do is, so we have plus 2, and then x, we raise the power by 1, so it becomes 2. And then we divide by the new power, so divided by 2. So that is the integral. So the integral of this is actually x cubed over 3 plus x squared. And you can see if you differentiate this with respect to x, you would end up getting 3x squared divided by 3, which is x squared, plus 2x, which is what we need. So that's the integral. And then this is between a and b. So what we do is we make like big square brackets, and then we put b on top here and a on the bottom here. And that just means that whatever the number for b is, so let's say b was 5, and let's say a was 3. Then we would put the number 5 into this first, so we would have 5 cubed over 3 plus 5 squared. And then you would subtract whatever is in here when you put a back into it. So you would have, let's say a is 3, so we have 3 cubed over 3 plus 3 squared. And that would be your final answer. That would be your answer for the area underneath the curve between a and b for the curve y is equal to x squared plus 2x. Now, let's say you didn't want to find the area. Let's say you wanted to find the area, but like it wasn't between any bounds. Let's say you just wanted to integrate. So remember, when you differentiate something, when you differentiate just a number, so a constant like 6, you get 0. When you differentiate another constant, let's say negative 35, remember, this is x to the power 0, this is x to the power 0. And you know what happens, right? It's like you do 0 times negative 35 times x to the power minus 1, which is still 0. So differentiating any number by itself, which just gives you 0. So when you integrate, you need to make sure that you add the integrating constant, which is a c. So make sure you always add a plus c, and this c can literally be any number. It could be 6, it could be negative 35, it could be anything. So if I tell you to calculate the integral of, so if I tell you to just do this, integral of 2x cubed plus x with respect to x, and I don't give you any numbers, I don't give you b and a, I just tell you to do this. The way you would do this is, you would do the exact same thing. So you would have the 2 in front, and then x to the power, 3 plus 1 is 4, divided by 4, plus, and then x to the power 1 plus 1 is 2, and then divided by 2. And then you would just add a plus c. That's it, that's all you have to do. Literally, just make sure you add the plus c, because when you differentiate this, you would get this back, but then you also have to differentiate something right here. And the c could be 0, but we always make sure we include it in there. So let's see why this actually works. Let's do an example of, let's do something that we can work with easily. Let's do a triangle, because we know how to calculate the area of a triangle. So let's say we had y is equal to x, right? Let's say that's our line, y is equal to x. Let's say that's 5, and that's 5. Right? Because y is equal to x, they would be matching. So this would be like 3, and that would also be like 3, right here. Let's say we want to calculate the area of this smaller triangle right here. So between 3 and 0. Well, how do we do that? We do base times height divided by 2. So we do 3 times 3, 9 divided by 2, which is 4.5. So that's our area. So we know this already. Can we do it by integration? So integration should give us the area, right? Well, we have y is equal to x. So I'm claiming that if you integrate the function, so if you integrate x with respect to x, between the numbers 0 and 3, because you're going from 0 to 3, you should get 4.5. Well, let's do it. So the integral of x is just x to the power 1 plus 1 is 2 divided by 2. And we don't need the plus c this time because we have actual numbers. So now we just do 3 and 0. So now we evaluate at 3 and 0. Well, what's 3 squared divided by 2? That's 4.5. Minus, what's 0 squared divided by 2? That's just 0. So we get 4.5. So that worked. What if we did between 3 and 5? Well, now it's not that easy because now we have a trapezium, right? So that's going to be difficult for us to do by hand. But now, instead of 3 and 0 right here, what if I just did x squared over 2? If I just did 5 and 3? Now this becomes faster than doing it by hand, like how we're used to doing it, because it's way more difficult to calculate the area for trapezium than just putting numbers into this right here. So you would have 25 over 2 minus 9 over 2. And that would give us 16 over 2, which is just 8. Look at how quick that was. So the area right here is 8. The area right here is 4.5. And does it make sense? Let's think about it. So that means the total area of this triangle is 12.5, right? Because 8 plus 4.5 gives you 12.5. But this whole thing right here is also a triangle. It's a triangle with length, with base 5 and height 5. And what's the area of a triangle with base and height 5? That would just be 5 times 5 divided by 2, which is also 12.5. So you can see this integrating thing is actually real. Like, it does work. And sometimes when a function is way more complicated, like this right here, or something that looks even more insane. Let's say we had something that looks like this. Let's say that's our function, right? And I want to find the area between here and here. How can I do that? There's no way for me to like do it with the rectangles. And that's when you would use integration. You would have the function given to you, you would integrate it, and you'd find the area between the 2 points, let's say C and D. So let's do like an example question, and perhaps it will make more sense. Well, honestly, with integration, you just have to practice enough and you'll get used to it eventually. So the diagram shows the curve of the equation y is equal to square root of x plus 4x to the power negative a half. The line y is equal to 5, so this is 5 right here, so write that down, intersects the curve at the points A 1, 5, so that's 1, and B 16, 5, so that's 16. Okay, so far we're good. Find the equation of the tangent to the curve at the point. Okay, so this is differentiation actually, because tangent means we need to find the equation of a line that looks something like this. So a line looks something like that. Well, let's see how we can get the equation of the tangent. So we know when you see tangent and curve, differentiation should go to your mind straight away. So dy by dx is equal to, well, power rule, so that would be a half times x to the power half minus 1 is negative a half, plus 4 times, well, now you have negative a half, times x to the power negative 3 over 2. Let's write it better, so that becomes 1 over 2 square root x minus 2 over x to the power 3 over 2. And we need the equation of the tangent at the point A. So A, the x coordinate is 1. So if you put 1 into here, we should get the gradient at that point. So we would have 1 divided by 2 square root of 1 is just 2, minus 2 divided by 1 to the power 3 over 2 is just 1. So that's that. So a half minus 2 is negative 3 halves. So we've made progress so far. So we have the equation y is equal to negative 3 over 2 times x plus c, because y is equal to mx plus c, and we already know m is negative 3 over 2. So how can we get c? Well, it's pretty simple, right? We know one of the point it goes through. We don't know this point, we don't know anything else, but we know it goes through the point 1 and 5. So when y is equal to 5, x is equal to 1. So 3 times negative 3 over 2 times 1 is just negative 3 over 2, and then plus c. Well, you can rearrange this to get c is equal to 5 plus 3 over 2. Well, that's just 13 over 2. And that's it. You have the equation of the tangent at that point is y is equal to negative 3x over 2 plus 13 over 2. So now we saw how differentiation can be useful for this curve. We can find the equation of the tangent at that particular point. Now let's look at the next thing. Calculate the area of the shaded region. So now we want to calculate the area of just this thing right here. So far with integration we learned that, let's say I had this right here. If I integrated this curve, I'd be able, so if I integrate this curve right here, so there's two different things. There's y is equal to 5 is a straight line, and then y is equal to square root of x plus 4x to the negative a half is this curve. And if I integrate the curve between 16 and 1, I should get all of this area right here. This thing, this thing, this thing, all of this area. But we don't want that area. We only want the area from here. So there's two ways to do it. So you can see this is a rectangle, right? This is just a rectangle of length 15 and height 5. So if I did 15 times 5, that's 75. That's the area of the whole rectangle, everything included. And if I subtract the area of the curve, the area underneath the curve from 75, then I'll be left with this area right here, which is the area that we need. So we can just do 75 minus area underneath the curve. Well, let's do that. And instead of getting 75 from there, we could just have y is equal to 5 as one of the other curves. So we could instead, well, let's do it both ways actually. Let's do the first way I said first so we don't get confused. So to calculate the area, we're going to do the integral of the function is x to the half plus 4x to the negative a half. So x to the half plus 4x to the negative a half with respect to x. And we're going to go from 16 to 1. Is that, I think those are the bounds. Yeah, 16 and 1. People say we're going to go from 1 to 16. Same thing. 16 to 1, 1 to 16. Just make sure you write it in the right order. So what will we get? So we use the reverse power rule. So we have a half. So we add 1 now. So we have x to the power 3 over 2. And we divide by 3 over 2. Well, dividing by a fraction means multiplying by the reciprocal. So that becomes 2 over 3. Plus 4x. And then we add 1 again, so it becomes positive a half. And then dividing by a half is like multiplying by 2, so that's times 2. And then, of course, between 16 and 1. Well, that's pretty simple. Now we have 2x to the power 3 over 2 over 3 plus 8 square root x between 16 and 1. And it's convenient that 16 is a squared number. So now we have 16 to the power 3 over 2 is just 4 to the power 3, which is 64. 64 times 2 is 128. So we have 128 over 3. Plus 8 times square root of 16 is 8 times 4, which is 32. So we have that. Minus, well, put 1 back in here. We have 1 to the power 3 over 2 times 2 over 3 is just 2 over 3. Plus 8 times the square root of 1 is just 8. So we have that. What can we do now? Well, we can just subtract. So we have 128 minus 2 over 3 is 126 over 3. That can be simplified. That is actually just 42. That's right, 42 on top, so I remember. Plus 32 minus 8 is just 24. So we have 42 plus 24, which is equal to 66. So that's the area underneath the curve. So that is this area right here. This whole thing is 66. Which makes sense that it's less than 75, right? Because this rectangle is 75. So now we want the area of just this thing right here. Well, if we did 75 minus 66, then we get that answer, right? Because just subtracting the areas. 75 minus 66, which is just 9. So that area right there, which there's no way you could calculate this without knowing integration, or at least so far, you'd get 9. You wouldn't be able to get 9 as your answer. Like, there's no way you can approximate that perfectly. And by integration, you can see that 9 units squared, centimeters, meters, whatever. But 9 square units is the final answer for that. And now what I was saying earlier is that you could do the difference between two curves. So y is equal to 5 is actually a curve as well. So y is equal to 5 is another curve. And y is equal to 4x to the half, or is it x to the half plus 4x to the negative a half? Plus 4x to the negative a half. That's the other curve, right? Yeah, x to the half plus 4x to the negative a half. So if I want to find the area and that's the difference, well, let's call this y1, let's call this y2. I can just do the integral of y1 minus y2 with respect to x between 16 and 1. And let's see if that gives us the same answer. So we would have the integral of 5 minus x to the half minus 4x to the negative a half with respect to x between 16 and 1. And you shouldn't be surprised when we get the same answer, because of course we'll get the same answer. So we get the integral of 5 is just 5 times x. Because this is 5x to the power 0 basically. So when you integrate this, you get 0 plus 1 is 1. So you have 5x to the 1 divided by 1, which is just 5. So 5x to the 1, which is 5x, minus x to the power 3 over 2 divided by 3 over 2 becomes 2 over 3, minus 4x to the half dividing by a half is times 2. And then this is all between 16 and 1. So let's see what happens now. So now we have 5x minus 2x to the power 3 over 2 divided by 3 minus 8 square root x, all between 16 and 1. So if you put 16 in, you get 16 times 5 is 80, minus 16 to the power 3 over 2 is 64 times 2 is 128, divided by 3 is 128 over 3, and then minus 32, because square root of 16 is 4, 4 times 8 is 32, and then minus 5 times 1 is 5, minus 2 over 3 minus 8. So let's see if you get the same thing. Well, you'd get, let's do it right here. You get 80 minus 32 is 48, sorry. So you have 48 minus 128 over 3. And then you're subtracting. 5 minus 8 is negative 3. So you have negative 3 minus 2 over 3. So that is equal to, well, we do 48 minus 3, so that's 51. That's nice to work with. And then you have minus 128 over 3 minus 2 over 3, so that's 130 over 3. So now we have minus 128 plus 2 over 3. Oh, sorry, that's minus 126 over 3. I don't know what I'm saying. Because you think minus 128 over 3 plus 2 over 3, so that's minus 126 over 3. And minus 126 over 3 is just minus 42. So now we have 51 minus 42, which is equal to 9. And that is what we got at the start here as well. We got 9 units squared. And in this case, it was easy to recognize that it was a rectangle. So we could calculate the area of the rectangle however we know how to do it. So just base times height, and then subtract the area of the curve from there. But let's say you wanted to find the area between two curves, right? Let's say you wanted to find the area of something like this, and then a curve that looked like this. Let's say you wanted to find that area right there. How would you find that? Well, you see this curve right here, we can integrate that. So you get the whole area right here, so this whole thing. And then you can subtract by the integral of this small curve right here that's underneath it. And that way you can get the area that you need. So you can see you can integrate between. So now you can't just, you can also find the area between two curves at this point. So let's say you wanted to find this area right here, that would just be an integral. But now this area right here is an area between two curves, because y is equal to 5 is technically a curve as well. It's a curve that's a straight line. So whatever you want to call it, but it's still a curve. So now you can see how important integration is and how useful it can be. So yeah, I hope you liked that video. It's a bit on the longer side. And with integration, you just have to practice a lot, and eventually you will see that it's not that bad at all. So, and we'll cover some more integration techniques for more complex functions in other videos. So yeah, like, comment, subscribe, and let me know what else you want to see in the future videos. Okay, let's talk about integration by substitutions. You can think of this as the reverse chain rule. So it isn't really, because remember, integration is just the opposite of differentiation. So everything is just reverse. So you can think of this as the reverse of chain rule. So what do I mean by the reverse of the chain rule? So let's say you had y is equal to, and let's make it a bit difficult. Let's say you had 2x plus 1. That's pretty easy. But then let's say you had it to the power 8. How would you integrate that? Well, one way to do is you can do 2x plus 1 times 2x plus 1 times 2x plus 1. You can do it 8 times, and then you will get a big polynomial with a power 8, 7, 6, 5, 4, 3, 2, 1, 0. And then you can integrate each term by term and then get the final answer. Or you can use integration by substitution. So what you do is, let u equal 2x plus 1. Right? You have u is equal to 2x plus 1. What's the derivative of u with respect to x? Well, that's just differentiating this term right here with respect to x. Derivative of 2x plus 1 is just 2. We should know that by now. And now let's rearrange this. So we're trying to find integral of y with respect to x. This is what we're trying to find, right? So if you rearrange this, if you bring dx to the other side, you have du is equal to 2 times dx. And then if you leave dx on its own, you have dx is equal to du divided by 2. So you have that right there. So now this becomes, so you had integral of y is 2x plus 1. So you have 2x plus 1 to the power 8 with respect to x. But now, instead of x, let's use u. So now 2x plus 1 is actually u. So now you have the integral of u to the power 8. And now instead of x, you have du over 2. So that becomes du over 2. Well, what can we do now? We can bring the half outside. So we have a half times the integral of u to the power 8 with respect to u. And this is a much simpler integral. This is a normal integral. You can use the reverse power rule, and you have a half times u to the power 9 divided by 9. And that's it. But there's one more step actually, because u, we don't want the answer in terms of u because we're always working in terms of x. But u is equal to 2x plus 1. You can just put that back in. So you have that is equal to a half times 2x plus 1 to the power 9 divided by 9, which is equal to 2x plus 1 to the power 9 divided by 18 plus c, of course, because it's a definite integral. So you can see, instead of expanding all these brackets out and you get an insanely long polynomial and then you integrate that and then you factorize that, instead of doing all of that, we can let u, this is also called integration by u substitution sometimes, because we let u equal 2x plus 1. Like how in a parametric differentiation we let t equal something, we let y equals something in terms of t and x equals something in terms of t. Now we have u is in terms of x. It's just, it depends on what you want to use. You can use u, you can use s, you can use t, you can use x. You can't use x. You can use anything else you want. So yeah, you let u equal the thing inside the brackets usually, and then you recognize that when you take the derivative of u with respect to x, you just get 2. and then you can rearrange. You can treat it as fractions even though they're not, and you can have dx is equal to du divided by 2 in this case, and then that becomes the integral of u to the power 8 with respect to u divided by 2. That's a pretty simple integral to do. You get u to the power 9 divided by 9. We multiply by the half that was outside, and now you have 2x plus 1 to the power 9 divided by 18, because u is equal to 2x plus 1. So you have to make sure you get the answer in terms of x at the end. And yeah, that's pretty much what it's about, but let's do a harder example, and then it will make more sense. We'll actually understand why it's so useful, because look at this curve right here. The diagram shows the curve y is equal to x plus 5 times the square root of 3 minus 2x, and its maximum point m, so we don't know what that is. Find the exact coordinates of m. Okay, so this is differentiation because that's a turning point. It says maximum point, so that means it's a turning point. Well, we don't even have to do integration. The first part is differentiation. So we find dy by dx. And here we can use the product rule, right? Because we have two different functions. You have x plus 5 as one function, and you have square root of 3 minus 2x as the other function. So what's the derivative of x plus 5 with respect to x? That's just 1. And you multiply that by the original square root 3 minus 2x. By the way, if this does not make sense, then you should watch the video on the product rule, because this is the product rule we're using here. So you have that, plus, and then you leave x plus 5 on its own. And then the derivative of square root 3 minus 2x with respect to x. Let's do that over here. So you have 3 minus 2x, I'll write it like to the power half. You want to take the derivative of that, so that becomes a half times negative 2 times 3 minus 2x to the power negative a half, which is equal to negative 1 over square root 3 minus 2x. So not that bad. So you can put that back in here. So you have negative 1 divided by square root of 3 minus 2x. And since the turning point, that is equal to 0. Well, what can we do now? We can just multiply everything by square root 3 minus 2x. So now you have, when you multiply everything by square root 3 minus 2x, you get rid of this right here, and then you multiply this by itself. So that becomes square root 3 minus 2x times square root 3 minus 2x is just 3 minus 2x to the power 1. You have that. And then you have plus, and then negative x minus 5. Because remember the negative 1 over there. And that is equal to 0. Well, 3 minus 2x plus minus x minus 5. So you can put the like terms together. So you have minus 3x minus 2 is equal to 0. And then you get x is equal to negative 2 over 3. Which makes sense because x will be on the negative side. So that's making sense so far. So you have x is equal to negative 2 over 3. Now what is y equal to? Because you need the coordinates. Well, it says it wants the exact coordinates, so we just put it back into the function how it is. So you have negative 2 over 3 plus 5 times the square root of 3 minus 2 times minus 2 over 3. So that becomes 3 plus 4 over 3. So that is, what is minus 2 over 3 plus 5? That becomes 13 over 3. And then here you get square root of 13 divided by the square root of 3. So you can write it as this right here. So you're left with minus 2 over 3 and 13 square root 13 divided by 3 square root 3. 13 square root 13 divided by 3 square root 3. And that's the coordinate. Those are the coordinates of the point M. Minus 2 over 3 and 13 square root 13 divided by 3 square root 3. Now the interesting part, using the substitution u is equal to 3 minus 2x. Okay, so it tells you what to use in this case. So you have u is equal to 3 minus 2x. Let's write that down again. Find by integration the area of the shaded region bounded by the curve and the x-axis. Give your answer in the form a square root 13, where a is a rational number. Okay, it's not too bad. So to find the integral, first we need to know what these numbers are right here. We need to know what this point is, and we need to know what this point is. Well, those points happen when y is equal to 0. So when x plus 5 times square root 3 minus 2x is equal to 0, those are the 2 points we need. So either this is equal to 0 or this is equal to 0. Let's start with this right here. So if x plus 5 is equal to 0, then x is equal to negative 5. Right? So that's negative 5 right there. And then for this point, hopefully it's positive. So we have square root 3 minus 2x is equal to 0. So we have 3 minus 2x is equal to 0 squared, which is still 0. And then x is equal to 3 over 2, which is positive. So that's good. So that's 3 over 2. So now we have the limits. Those are called the limits. And those are the limits of the area of the region we are integrating over. So we have the integral between -5 and is 3/2. Yeah, it was 3/2 of y with respect to x. Okay, so far so good. We have u is equal to 3 minus 2x. So now what's du by dx? Because that's the first step. Well, that's just the derivative of this with respect to x. So this goes away, this becomes 0, and this becomes -2. This is just simple power rule. Now we can rearrange, so we can let du is equal to -2 times dx. And then dx is equal to -du divided by 2. So far so good, nothing too difficult so far. So now what do we have? We have the integral, and I'm going to leave the limits out because you will see why these are actually not the correct limits for this function. So you have the integral of y. Well, what is y? Y is x plus 5. So we have x plus 5. And then we have the square root of 3 minus 2x, which is the square root of u, because u is 3 minus 2x. So you have x plus 5 times the square root of u. And then instead of dx, let's write du. So we have -du divided by 2. So far not too bad. But we still can't integrate this with respect to u because we have an x right here. We don't want an x. We want a u because that would make everything in terms of u, and then we can integrate that. So since u is equal to 3 minus 2x, we can just rearrange. We can have positive 2x is equal to 3 minus u. If you just bring 2x to one side and u to the other side, you have that, and then you have x is equal to 3 minus u divided by 2. So you have that right there. So now you have the integral. So let's put the minus half right here. So you have minus a half integral of x plus 5. So that's 3 minus u divided by 2 plus 5 times the square root of u with respect to positive u this time because we brought the negative outside. Well, we can simplify this further. That becomes the integral of 3 minus u over 2 plus 5 is 13 minus u times the square root of u, and then divided by 2 du, and then we obviously have the negative a half right there. Okay, so far so good. Still remember, there are no limits because those will change. Now, we can bring the half over here outside, so we have -1/4 integral of, and we can expand the bracket, so we can have 13 square root of u minus u times square root of u is u to the power 3/2. It's just simple indices with respect to u. And now you see we can actually start integrating because this is all in terms of u. We have got rid of x, and this is an integral that's very easy to do with just the reverse power rule. Whereas if you had to integrate this right here, yeah, good luck with that. I don't know how you're going to integrate that without u substitution. So now you have this right here. Now, what do? Well, we just integrate. So we have -1/4 outside, and then we have 13 u to the half. If you integrate that, that becomes 13 u to the power 3/2 divided by 3/2, so that's times 2/3, minus u to the power 5/2 divided by 5/2, so that's 2/5. And now we need some limits. So can we use -5 and 3/2? Well, we could if you want to put u back as x. So if you like what we did in the first example right here, at the end we put x back into this thing for u right here because u is actually in terms of x. So we put 2x plus 1 back here, and then we got our answer. But now this is a definite integral, so we need some numbers. Now what we can do is we can put the 3 minus 2x back in for u right here, and then we can use -5 and 3/2. But the other way to do it is, if you have u is equal to 3 minus 2x, then you have the lower limit is equal to 3 minus 2 times the value for x was -5 right here. So you have -5, and that is the lower bound, that is equal to 13. And then you can use the upper bound as u2 is equal to 3 minus 2 times x, which is positive 3/2. This just goes to 0. And you can use that as the upper bound. So instead of putting everything back in for x and then it's going to look messy and everything, you can just put in 0 and, no, you're going to put in 13 and 0 over here. This seems counterintuitive because why is the 0 is bigger than 13 is bigger than 0. So why is 13 at the bottom? But then you can't change the order around because over here we had -5 at the bottom, and when you put -5 back into x right here, you get positive 13 for u. So you have to make sure you put it still at the bottom. And then for here, instead of 3 over 2, we got 3 minus 2 times 3 over 2, which becomes 0. And you put that at the top because 3 over 2 was at the top. So now we have those limits right there. And actually, this is much easier to evaluate because now you have negative 1 over 4. And then when you put 0 in for u, everything just goes away. So you have 0 minus, now is the interesting part. So we have 13 times, you put 13 back in for u, you have 13 to the power of 3 over 2. Well, that's just 13 times root 13. So that becomes 26 over 3. That's just, wait, let me leave that bracket open. If you do 13 times 2 over 3, that's just 26 over 3, right? So you have 26 over 3 times, this is 13 root 13. So this becomes 13 square root 13. Minus 2 times, well, 13 to the power of 5 over 2, I'll tell you right now, is equal to 13 squared times root 13, which is equal to 169 times root 13. You can put this in the calculator if you want, you will see it's the exact same thing. And this is divided by 5. And then you can like put the square root of 13 outside, so you can have negative 1 over 4. And then you have square root 13, because you can factorize square root 13 out from here. And then you have 26 times 13 divided by 3 minus 169 times 2 divided by 5. And once you evaluate all of this, I'll let you have it in my book, so I'll just say the answer. So you'll end up getting something like negative 676 over 15 times negative 1 over 4 square root 13. And then once you simplify that, you'll end up getting 169 divided by 15 square root 13, which is in the form we want. We want it in the form a square root 13, where a is a rational number. So in this case, I guess our a, you can specify it if you want. A is equal to 169 divided by 15. But it's all, you don't have to specify it. You don't have to make this well known because it's already implied that you're giving it in the form a square root 13. So if you have the square root 13 there, then a is 169 over 15. But yeah, that's integration by substitution. Sorry, not by parts. By parts is the next video. So you might be asking, how do I know what I should use? Like in this case, why didn't I use x plus 5 as my u? And I'll show you how to actually think about it. Let's do it over here because there's more space. So let's say you had the integral of, and I'm gonna rely on you knowing that the derivative of sine is cosine and derivative of cosine is negative sine. So if you take the integral of sine, you get negative cosine. Like it's just the opposite. So like we know that the derivative of sine of x is equal to cosine of x. That means the integral of the cosine of x with respect to x is equal to sine of x. Of course, right? Remember, it's just the opposites. Like what do you differentiate to get sine? Well, you find that. Or what do you differentiate to get cosine? It's just the opposite of what we already know. So let's say you have to do the integral of sine of x times cos of x with respect to x. So how do I know what to let u equal? Do I let u equal sine of x or u equals cos x? Well, in this case, it doesn't really matter. But what you will realize is that what you actually have here is a function times the derivative of itself. You can see that right here. So in this case, maybe it's harder to see, but this function right here, its derivative will be something in terms of this right here. It's very difficult to see right now. But what you can do is, so in this case, let u equal sine of x. Because what you will notice now is that when you do du by dx, you get cos of x, and then you get dx is equal to du divided by cosine of x. Well, then you get the integral of, well, sine of x is u, and then instead of cos of x, well, you can write cos of x right here, and then instead of dx, you have du divided by cos of x. Du divided by cos of x. And these will just cancel out. So you're left with the integral of u with respect to u, and that's very simple. That's just u squared over 2. And then u is actually equal to sine of x. So you have sine squared of x divided by 2 plus c. That means when you differentiate sine squared of x plus 2 plus c, sine squared of x divided by 2 plus c with respect to x, you'll end up getting sine of x cos of x, and you can try it. We find the derivative of, we're not going to do plus c because we already know that's a 0. So the derivative of sine squared of x divided by 2, well, that's just a half times the derivative of sine of x and sine of x again. And now you can use the product rule, and you get a half times cosine of x, sine of x, and then you have plus a half cosine of x, sine of x. And of course, a half plus half is just 1, so you have sine of x, cosine of x. And that is exactly what you want. So you have to realize that when you're looking at these functions, look for a function and then try to look for its derivative. Sometimes you'll be told what substitution to use, like in this case, because this was a pretty difficult question. But sometimes when you have sine of x, cos of x, just think, well, it doesn't really matter what you did, because if you did u is equal to cosine of x and then you took that, you just get positive or negative u. It would end up being the same answer, of course. But just have to realize that when you, the whole point behind this is that the derivative is already hiding inside this right here. And you just have to think, okay, what function can I take the derivative of that I'll end up getting its derivative, which is already in there. So yeah, just do some practice with it and eventually it will make sense to you. It's not that difficult. Just try different questions, make your own questions, do your own substitutions, or like for this case, try using u is equal to x plus 5 and then try using u sub from there. You will see it's much harder, but you will get the same answer. So yeah, like, share, comment, and subscribe, and let me know what else you want to see in future videos. Okay, so let's talk about integration by parts. This is the final tool you need to be able to integrate anything that can be integrable. So remember the product rule from differentiation. So if you had fg prime, that's equal to f prime g plus fg prime. Remember this from the product rule. Now, integration by parts, the formula is usually given with in terms of u and v, but u and v are just f and g, so it doesn't matter. But let's write that f and g in terms of u and v. So I'm doing the exact same thing. I'm writing uv all prime is equal to u prime v plus u times v prime. Okay, so what can we do? Let's integrate both sides. So when you integrate both sides, you integrate this, and you integrate this. Well, uv prime and then integrate. It's like differentiating something and then integrating it. Well, when you do that, you just end up getting the function that you started with. So that's uv. That's equal to, now we leave this how it is. So we write that as u prime v plus integral of u v prime. And then what we do is we bring this to the other side. So we're left with uv minus integral of u prime times v is equal to integral of u times v prime. Now, the thing is, the formula is usually given like this. So like this is the final formula. But remember, u is a function in terms of x. So u is equal to something in terms of x. And v is also equal to something in terms of x. It's a functions, right? So another way to write this is equal to the integral of u. V prime is just dv by dx as a derivative of v with respect to x. And that is equal to, well, you have uv, so just write that u and v, minus the integral of v, and then u prime is just derivative of u with respect to x, so you write that as du by dx. Now this might not make a lot of sense right now, but let's say I ask you to integrate something like 2x times sine of x dx. Now what do we know so far? We know the reverse power rule and we know integration by substitution. And none of these would work, because what can you even substitute in this right here so that integration by substitution would work? There's really nothing you can do. So now this is the reverse product rule, because now we have a product of two functions. So we have the functions 2x and we also have the function sine of x. Let me draw that better. We have 2x and then we have the sine of x is the other function. So if you compare, you can write 2x sine of x and u dv dx. Well, how do I know what is u and what is dv by dx? So this is how you usually choose u. So u, you do this, it's called Lie8. This is just like an acronym for, I'll show you right now, Lie8. This is logarithmic functions. This is inverse functions. This is algebraic functions. So like x right here that we see. These are trig functions. And these are exponential functions. Exponential. So we choose u to be whichever the first of these is. So in our case, we have 2x and we have sine of x. Well, 2x is an algebraic function, so this is 2x. And then sine of x is a trig function, so this is sine of x. So what we do is we let u equal 2x. So let u equal 2x. That means our dv by dx is going to be sine of x. So we have dv by dx is equal to sine of x, right? Of course, because if u is equal to this, then we're left with du by dx, so it has to be equal to that. So now we need two more things. We need du by dx because we're going to use this later on. So it's better to have everything that you need first before you start using the formula. Because we're going to have du by dx here. So we need du by dx, which is just 2. And then we need v as well. Well, v is just the integral of the sine of x. That's pretty simple. That's just negative cosine of x, right? That's a very simple regular integral. So now we have everything we need to actually apply the formula. So the integral of 2x sine of x is equal to the integral of u dv dx, which is equal to uv. So we have u times v. So we have 2x times negative cos x. So we have negative 2x cos of x minus the integral of v, which is negative cos x, times du by dx, which is positive 2. Of course, with respect to x, right? And now look, this is negative 2x cos x, so we're done with that. And now this negative becomes plus 2. You can bring the 2 outside because it's just a constant, right? Then you have the integral of cosine of x dx. And this is very simple. We know what the integral of cosine of x is, right? That's just equal to the sine of x. This is one of the simple integrals, equal to sine of x. And that's it. That's all we really needed. So now we have that is equal to negative 2x times the cosine of x plus 2 times the sine of x plus c, of course. And that's your final answer. And you can see that it works. So let's differentiate this right here, right? We're going to find dy by dx. And that is equal to, well, let's use the product rule because, of course, that's how you differentiate a product of two functions, right? So we have negative 2x cos x. So if you differentiate that, you get negative 2 cosine of x plus, and you have negative 2x, and the derivative of cosine of x is equal to negative sine of x. So we have that plus 2 times the derivative of sine of x is cosine of x. Well, you can see this and this will cancel each other out, and negative will make a positive, so you'll be left with 2x sine of x, and that is what we started with. We started with the integral of 2x times sine of x dx, and that's exactly what we ended up getting. So you can see that the integration by parts helped us to integrate a product of two functions, one of which is actually the derivative of another function. So if you just see this formula right here, you have to kind of memorize this formula because it is very helpful, but you can always derive it by yourself. Just look at the product rule. This is very simple to memorize. This is very, very simple. You take the derivative of one function, leave the other function as it is, and you add that to the first function, however it is, plus times the derivative of the second function. From there, you just integrate, and then you end up getting integration by parts rule. And then to choose u, well, you use this right here. This whole thing right here. It's called LIATE because it's like an acronym to remember, LIATE. And you can see, you let u equal whatever the first of these end up being. So in our case, we had 2x and sine of x. 2x is algebraic and sine of x is trig. Well, algebraic comes before trig in this case, so we let u equals 2 of x, and then we let dv dx equal sine of x. And then from there, we find du dx and we find v, and then it becomes very simple. And we just take regular integrals, and we end up getting our answer. So let's do an example question, and it'll make even more sense. The constant a is such that the integral, the definite integral between 0 and a of x e to the negative 2x dx is equal to 1 over 8. Should the a is equal to a half ln 4a plus 2? Okay, this is a very nice question. So, remember, LIATE, right? By the way, first you have to realize this is integration by parts because it's a product of two functions. We have x, and we have e to the negative 2x. Those are our two functions. So we have LIATE. Well, clearly e to the negative 2x is exponential, so we have e to the negative 2x. And then x is just algebraic, so this is x. So that means our u is going to be equal to x. That means our dv by dx is going to be equal to e to the negative 2x. Okay, before we start using the formula, let's find du by dx. That's just 1, because if you differentiate this with respect to x. And then let's find v, and that's going to be equal to the integral of this, which is negative e to the negative 2x divided by 2. So now we have all that we need. So let's start using the formula. So the formula says you do the integral of u dv dx is equal to uv minus the integral of v du dx. Okay, let's start then. So we have u times v, that's x times negative e to the negative 2x divided by 2. So we have negative x e to the negative 2x divided by 2 minus the integral of v, which is negative e to the negative 2x divided by 2, times du by dx, which is just 1. So that's it. That's right there. And this is, of course, with respect to x. Now what do? Well, negative negative becomes positive, and we can bring the 1 over 2 outside. So we have negative x e to the negative 2x over 2 plus a half times the integral of e to the negative 2x dx. Well, we already know what this is, right? We can calculate it again, but we know the integral of that is just negative e to the negative 2x divided by 2. So now we have negative x e to the negative 2x divided by 2 plus a half times negative e to the negative 2x divided by 2, which is equal to, well, let's factorize it, right? So you have e to the negative 2x divided by 2. This is the good thing with e, you can always factorize the integral to the end. Then you have negative x plus, and then you're going to have a negative a half, I think. So let's make the negative right here. You're going to have positive x plus a half. Is that correct? Negative x e to negative 2x divided by 2. Negative x e to negative 2x divided by 2. Minus e to negative 2x divided by 4. Minus e to negative 2x divided by 4. So yeah, that's it. That's our answer right there. But now what do we need to actually do? We found the integral. We need to put in the limits and see. And it's telling us the answer is going to be 1 over 8. So if you evaluate this between a and 0, then you should end up getting 1 over 8. So let's do it. And then we have to find the value of a. It actually tells us what it is. We just have to like show that it's true. So let's try. So you have negative e to the negative 2a divided by 2. I'm just putting a in for x over here. And then you have a plus a half. And you have all that in brackets. And then from there you subtract. When you put 0 in here, you get e to the 0 is just 1. So you have negative a half times 0 plus a half. So you have negative 1 over 4. And that is equal to 1 over 8. Okay, so what can we do? We can rearrange. So this is negative, negative. So that's a positive a quarter. I bring that to the other side. So we have 1 over 8 minus a quarter. So we have negative e to the negative 2a. And I'll write this as 2a plus 1 divided by 2 is equal to, I know this is divided by 2, I'll just bring 2 to the other side. So we have 2 times 1 over 8 minus 1 over 4. Okay, so what's that? So we have negative e to the negative 2a times 2a plus 1 divided by 2 is equal to 1 over 8 minus 1 over 4 is just negative 1 over 4. Or negative 1 over 8. And then that times 2 is just negative 1 over 4. So we have negative 1 over 4. Well, we can get rid of the negatives, right? Because there's negative here and negative here. So we can make that positive. We can make that positive. Okay, so far so good. Now we can multiply this by 2, right? So we have e to the negative 2a times 2a plus 1 is equal to 2 over 4, which is a half. Okay, and that's all we can do with just regular manipulation. Now we need to use the natural log because we need to get a on its own. So how do we do that? Well, let's take the natural log of both sides. So we have ln of this whole thing right here. That's ln e to the negative 2a plus 1 is equal to the ln of a half, which is equal to negative ln 2, right? What do we know? This is ln a times b, which is ln a plus ln b. So that is ln e to the negative 2a plus ln 2a plus 1 is equal to negative ln 2. Now what do? Well, ln e to the negative 2a, we can bring negative 2a over here, negative 2a, and then ln of e, which is just 1, so we have negative 2a there, plus the natural log of 2a plus 1 is equal to negative ln 2. Now what do we need to do? We need to get to this form right here, a half ln 4a plus 2. Okay, how do we do that? Well, ln 4a plus 2. So what we can do now is we can bring this 2a to the other side. So we have ln 2a plus 1 is equal to 2a minus ln 2. Right? Yep, we have that right there. Okay, and now what can we do? Well, we just need to rearrange more. So we have ln 2a plus 1 is equal to 2a minus ln 2. Let's leave 2a on its own. So then you'll have ln 2a plus 1. Bring the negative ln 2 to the other side. So you have plus ln 2 is equal to 2a. Well, this is again ln a plus ln b. So if you just multiply them, you end up getting ln a times b, which is ln 2a plus 1 times 2 is 4a plus 2. And that's equal to 2a. And then you've got what you need if you divide by 2. So you have a is equal to a half times ln 4a plus 2. And that is exactly what we needed to show right here. A is equal to half ln 4a plus 2. So yeah, that's integration by parts. This is probably the most important form of integration, because most of the times you're not just going to be able to ask the integral of cosine of x, right? That's very easy. But as soon as I say the integral of sine of x cosine of x, well, this is interesting because now you can do it two ways, right? You can do it by integration by substitution, and when you get the answer for that, which is equal to sine squared of x over 2 plus c, try using integration by parts and see if you end up getting the same answer. Actually, I might make a short video doing that by integration by parts. So yeah, I hope you enjoyed the video. If you did, please like, share, comment, and subscribe, and let me know what else you want to see in future videos. A short video on integration by parts. So we have the integral of sine of x cosine of x dx. If you did this by substitution, you end up getting the answer as sine squared of x divided by 2 plus c. So that is integration by substitution. Now let's do integration by parts and see if we get the same answer. So now we have sine of x and cosine of x. So these are both trig functions. It doesn't matter what you make u and what you make dv by dx. So in our case, let's just make u is equal to the sine of x, and then dv by dx is equal to the cosine of x. Okay, and then that means we need to find du by dx and v before we start doing anything. So du by dx is equal to the cosine of x, and v is equal to the sine of x. Right there, okay. So now we have the integral of sine of x cosine of x dx. We have all the things that we need. We just need to apply the formula. So the formula says the integral of u dv dx is equal to uv minus the integral of v du by dx. So we have everything we need. So I'm going to do something. I'm going to call this integral I. I'm going to call I is equal to the integral of the sine of x times the cosine of x dx. And you will see why soon, because, yeah, you'll see. So now what do we have? We have that is equal to uv. So we have sine of x times sine of x. So that's sine squared of x minus the integral of v times du dx. So we have v, which is sine of x, and then du dx is equal to cos of x. We have sine squared of x minus the integral of sine of x times the cosine of x with respect to x. So what's happened right here? Well, we've applied the formula, but then we have ended up getting something which is still very difficult to integrate. We still need to use integration by parts for this, because this is also a product of two functions, right? But this right here is actually our original integral, so, which is equal to I, right? So we have I is equal to the sine squared of x minus I, right? Because that is the integral that we need. So now all of that's gone away. So now we can rearrange it. So we can have 2 times the integral. So 2i is equal to sine squared of x. And then what do we have? If you divide both sides by 2, we have I is equal to sine squared of x divided by 2. But what is I? I is the integral that we needed. I is equal to the integral of sine of x cos of x dx. So that means the integral of the sine of x times the cosine of x with respect to x is equal to the sine squared of x divided by 2 plus c, of course, always. And that is exactly what we would get if we integrated by substituting u is equal to sine of x and then we found du dx. So you can see the integration by parts can work. As soon as I make it more difficult, as soon as I say the integral of x e to the x dx, well, now substitution's out of the window. You don't know how to substitute, right? But using integration by parts, you can easily get that done. So you can see why integration by parts is such a useful tool. So I hope that makes sense. Just a quick video on an application of integration by parts. So yeah, like, share, comment, subscribe. Let me know what else you want to see in future videos.